Hello scholars, it's Edomat Hub. In this video, we're looking at full breakdown of AC circuit for your JAMB exam. Now, take note of something. Now, AC here means alternating currents. That's the meaning of AC. And there are basically two types of currents. So we have the one that's called DC current and another one called alternating current. So DC current is a constant current. It does not vary with time. So in DC current, you have like the vertical axis could be like this. This will be the horizontal axis. This vertical axis here could be the voltage or the current. So the current and the time, they have this relationship here. So there's a straight line like this. So this is the current. The current does not change with time. Here, assume the time is 10 seconds. The current could be like maybe 10 ampere. When the time is 20 seconds, the current is still 10 ampere. So that means that the current does not change with time. Unlike in AC, this is AC here. This vertical axis could be V or I, while this horizontal axis could be time. So you can see in this case that the current is changing. This could be I naught or this could be V naught. So two of them are changing. You can see where the current is going. At this point is positive, at this point is negative. So you're doing the maximum called I naught. This will be minus I naught or minus V naught. So this V naught here is called the peak voltage. The peak voltage. Why I naught be the peak current. Okay, peak current and peak voltage. So this graph just shows you that the current is changing with time, unlike what you have in DC, where the current does not change with time. AC stands for alternating current. And from this graph, the instantaneous current or the instantaneous voltage is given by I is equals to I naught sine omega t, while V is equals to V naught sine omega t. So this I here is the current at a particular time interval, maybe the current at a particular time. That is this I. This I naught is the maximum current that you can get. The same thing with this V naught, the maximum voltage you can get. So I naught is called the peak current. V naught is the peak voltage. This omega is angular frequency, while the t is the time. You understand? So this omega has its own formula. Omega is equals to 2 pi f. Okay, so just keep that in mind. And there's something called the IRMS value, which is written as IRMS. It stands for root mean square current. Root mean square current, and it is related to this I naught or V naught by IRMS is equals to I naught over root 2. Then you also have VRMS is equals to V naught over root 2. So what is the meaning of this IRMS? This IRMS, it is the value of the AC current that will act as a direct current when it is connected to the same resistor. So it is defined as the value of the DC current that will have the same heating effect in a particular resistor as the AC current. So this is the formula that joins the two of them. You can also write it like this: I naught times 0.707 V naught times 0.707. That is because 1 over root 2, if you divide it to calculator, you will get 0.707. So this 1 over root 2 here, this part here, this 1 over root 2 here is 0.707. So you can say IRMS is equals to I naught times 0.707. The same thing with VRMS. And there are three components that I always use in an AC circuit. So you have the resistor, capacitor, and inductor. So let's look at them one by one. Part which is pure resistor in an AC circuit. So we're looking at resistor-only circuit. The resistor-only circuit is an AC circuit that contains only resistors. Normally, AC circuits normally contain capacitors, inductors, and resistors. But now we're looking at the ones that contain only resistors. So it should look something like this. You have a resistor like this, then connected to an AC source. So you see this symbol, then a circle like this. That's the that is an AC source. The current or voltage is changing. Then you can have something like maybe an ammeter here and so on like that. But let me just ignore the ammeter part. Let me just draw it straight up like this. So this part here is a resistor. You can also have a voltmeter here connected like this, but I'm going to ignore that one too. So there will be a current flowing here, and there will be a voltage across this guy, this resistor here. You can see that it has only resistor, nothing else is connected to it. Now there are some features that we apply here. Please take notes and listen carefully. The first thing to note is that according to Ohm's law, the Ohm's law is V equals IR. So don't forget that the V here can be V naught. If the V becomes V naught, this I will also change to I naught, and this one will be R. If the V change to RMS, the I2 will change to IRMS. Then this one will just be R. So V naught equals I naught R. VRMS equals IRMS R. Please take note. You cannot use VRMS here and use I naught here. They must follow V naught, IRMS, IRMS. Okay, I understand. Do you get that one? Okay, thank you. The next one, about 2. The next thing to note here is that the peak voltage, sorry, this is peak voltage here, like I've done. The next thing to note is that there is power dissipation. There is power dissipation. There is power dissipation. That means after a while, dissipate. After a while, this resistor here to get hot. Once it gets hot, power will be dissipated. That means you can have your power as I squared R. The I you're going to use in this formula is not I naught. It is the IRMS value you're going to use to find the power if you're looking for power. So the power here, the power in this case will be IRMS, the IRMS value of the power. Square it, then multiply by the resistance. Power is I squared R normal. Power is I squared R normally. So the power will be I squared RMS value. Okay, then multiply by the resistance. Okay, hope you understand that one. So there is power dissipation because it is only a resistor circuit that dissipates power, in the sense that after a while this resistor will become hot. Take note, a circuit that has only capacitor or a circuit that has only inductor, they do not dissipate power. No, there's no loss of power. No power dissipation in a circuit that contains capacitor or inductor. It is only a circuit that contains resistors that there is power dissipation. Look at the formula for power. Power is I squared R. The R here is not capacitor, it's not capacitance, it's not inductance, it's only resistor. So the power dissipation depends on the resistance. Okay, the next thing to note here is that the voltage and current, that's V and I, voltage and current are in phase. That means they move together. No one is gapping the other one or leading the other one. No one is lagging. So it looks something like this. The voltage, the vector diagram, they might ask you to draw the vector diagram. JAMB have asked it before. Vector diagram of an arrow-only AC circuit. If you draw it like this, see how it will be. The voltage is going like this. The current too is going in that same direction. So this one can be current I. This one is I, and this one is voltage. Two of them are in the same direction. That's because no one is leading or no one is gapping the other one. They are in phase. If you draw the waveform, if you want to draw the waveform to understand it better, it will look like this. If this one were to be the voltage, let me assume this red line, this red waveform is voltage. Can you see the way it's going? If I draw the one for current, let me change the current to maybe green color. The one for current too, we go the same way. It will follow the way this one went, it will go the same way. It might be higher than it, does not matter. So at this point, this one too will do 0. The current will do 0 at this point too. You do 0. When the voltage is doing 0, they will meet at this point. It will also go like this and meet here. Like that. When they are doing 0 or they are doing maximum at the same instance, this green line is the current. This red line, this red waveform, this red one is the voltage. You can see that when the voltage was doing 0, current 2 was doing 0. Both of them went up, though the current was higher than it. But they did 0 at the same time here. They did minimum at the same time here. They did 0 at the same time here. They did maximum at the same instance here. So that means they are in phase. They are together. They are moving together. No one is gapping the other one. No one is leading. No one is lagging. They are in phase. Take note, in the current and voltage are in phase. So they might ask you for phase angle. Phase angle in this case is 0. Phase angle in an arrow-only circuit, the phase angle theta is 0 degrees. Okay, I hope you understand that one. Then what else again? So these are the key points I want to know. Let me revise it again. The first one is that according to Ohm's law, V equals IR. In this case, your V naught will be I naught R. V naught here, I naught here. V RMS here, I RMS here. You understand? There is power dissipation. After a while, the resistor will be getting hot. And what's the power? The power is I square RMS. Or you can also use IV. But the I and the V will be RMS value. I RMS multiplied by VRMS. That will be the power. Please don't use I naught to do power. use the IRMS values. Then V and I are in phase. Current and voltage are in phase. They move together. You can see the vector diagram, same direction. So this will be VR. This will be IR. Voltage across resistor straight up going like this. Current across resistor. Current across resistor going like this. Two of them are in the same direction. You can see the waveform here. This waveform, this place can be V or I. So you can see both of them did maximum, minimum at the same time. Okay, so I hope you understand this one. Okay, so let's move on to the next one. Next one will be capacitor-only circuit. So let's see what that one looks like. So the voltage, then let me just add one more thing. There will be resistance here. You can see the resistor is contributing the resistance. That is the opposition to the flow of the current. So here in this circuit, we're talking about resistance. Okay, so we'll be seeing what we'll be talking about when we do capacitor and inductor. So that's the basis for this one. Next one, we'll be looking at the capacitor only circuit, an AC circuit that contains only a capacitor. So look at the capacitor here. This is a capacitor here. Then this capacitor here, there is an ammeter here to measure the charge or the current that is going to the capacitor. This is voltage AC source here. Okay, this one is the voltmeter to measure the voltage across the capacitor. Please follow up. All right, what I'm going to do in this case is that this capacitor here, in this circuit, don't talk about resistance here. Nothing like resistance here. You cannot see anything that's due to resistance here. There's no resistor here. But this resistance is the opposition to the flow of the current. But this capacitor too must also oppose the flow of the current. But you're not going to talk about resistance. You're going to be using the word reactance. Okay, so reactance is the opposition offered by the capacitor to the flow of the charge or current through it. Okay, so this reactance, it has a name for a capacitor. It is called capacitive reactance. Reactance is just like an opposition. So the symbol is XC. This is like the resistance of a resistor. Don't let it confuse you. This word here is like the resistance that a resistor will offer. The resistor will have to block the current. So capacitor too will block the current, but you're not going to call it resistance. You call it reactance. So this capacitive reactance, the formula is 1 over omega C, or you can say XC is equals to 1 over, your omega is 2 pi F. This formula here is the formula for the capacitive reactance of a capacitor when it is in an AC circuit. The unit of this reactance is ohms. Take note, unit of reactance is ohms. Just like unit of resistance too is also ohms. Okay, so in this circuit, your Ohm's law to also apply. So your Ohm's law is V equals to IR, but you cannot write R here because there's no resistor in this circuit. There's no R here. So that R will turn to XC since that's the opposition is offering to the flow of the charge. So I'm going to write V equals to IXC. If this V now is V naught, this one will be I naught. V naught is equals to I naught XC. If the V turns to RMS, this one will be VRMS. What would this one turn to? Hope you know. Yes, you are correct. IRMS XC. But this thing is not time, so it means XC. These are the formula for the applying Ohm's law to a capacitor. So keep this on in mind. Don't forget it, or keep it in mind. It's very, very important. I'm going to use it. Now, but is there power dissipation here? Is there power dissipation? Like what I told you, ask yourself, is there power dissipation? So the answer is no. There's no power dissipation. No power dissipation. So that means that nothing like I square R here. Forget about power dissipation. A circuit that contains capacitor or inductor does not dissipate power. It's only circuit that contains resistor that dissipates power. And since there's no resistor here, forget about power dissipation. No power dissipation in this circuit. Then the next point is, how does the current and voltage, as in, how are they moving? Which one is lagging? Which one is leading? Don't forget that the capacitor stores charge. Capacitors, they store charge. Now, since they store charges, that means the current will be leading. So let's draw it down. So the current is leading. So I'm going to start the current from like here. But okay, let me draw voltage first so it's not confuse you. Let's assume this is the voltage. This voltage across the capacitor, that will be VC. Abi. Now let me draw IC, the current. I'm going to use red color for that one. Now the voltage is starting from 0, Abi. If the voltage is starting from 0, the current cannot start from 0. The current must lead. You understand? The current must lead the voltage. So that means the current will start from around here. It will start at an upper value. This is 0 here. Voltage is starting from 0, but current will start from a higher value. I hope you understand. So the current can come something like this. So on like that. So you see that this one here is the current. This is IC. While this blue line is VC. You will see that the current is leading because I told you that to know which one is leading, just look at what are the two of them doing at the origin. Just check for me at the origin. You see that this blue one, which is the voltage, is 0. But what is current? Current is higher than it. Current already has a value, maybe like 10 amperes or whatever. It's already high. You understand? So current is leading. So in a capacitor circuit, in the capacitor-only AC circuit, the current leads the voltage by the phase angle is pi over 2, or you can say 90 degrees. So in a pure capacitor circuit, the current leads the voltage. The current is gapping the voltage. The current is in front of the voltage. Anyhow you want to put it, the current is gapping the voltage by pi over 2 or 90 degree. Or you can say the voltage is lagging the current. That means the voltage is at the back of the current. Anyone want to put current is leading. Take note in an AC circuit for capacitor, current is leading. Capacitors store charges, so you can use that idea. Charges is the same thing as current. So capacitors store charges. So you just use that one to like remember it, that current is leading the voltage and the phase angle is pi over 2. Now what will be the vector diagram? What does the vector diagram look like? The vector diagram look like this. So you draw the VC, the voltage across capacitor, draw it down because it is lagging. It is lagging. Draw it down. Let it face down. In vector diagram in this topic, anything facing down is lagging. Then draw the IC, the current through the capacitor. Draw it like this. So you now put one arrow going like this. This arrow here, you can see the phase angle. The angle between two of them is 90 degree or pi over 2. Pi over 2 is the same thing as 90 degree. This is pi over 2 radians. Same thing as 90 degree. So the voltage is lagging. So it is facing down. Capacitor voltage is lagging to face down. Current voltage will face horizontal like this. So the angle between them will be 90 degree. This is the vector diagram for a capacitor-only AC circuit. So if you have a capacitor in an AC circuit, the vector diagram would be like this. You understand? That means the current will be leading the voltage. So I hope you understand. Alright, the next one will be inductor-only circuit. Let's see what it's going to look like. This one is an inductor. So inductor-only AC circuit. That's an AC circuit containing only an inductor. So this is the symbol of an inductor. So I'm just going to connect it to an AC source. Then maybe to an ammeter to measure the current. Then a voltmeter to measure the voltage across the inductor. Sorry. And an inductor has something called inductance. So just the way a resistor has resistance and a capacitor has capacitance. So the value of an inductor is measured in, like, the unit of the inductance is Henry, and the symbol for Henry is H. So this is an inductor here connected to an AC source. This is the ammeter measuring the current. This is the voltmeter measuring the voltage. So there's no resistor here right now. So the inductor will offer a resistance to the current. To offer a resistance. So that resistance is called reactance. But not just any reactance. You call it capacitive. You call it inductive. This is not the one for capacitor. You call it inductive reactance. So inductive reactance, the symbol is XL. You understand? Just like capacitive reactance, symbol is XC. So the resistance that the inductor will offer is called inductive reactance. It's also measured in ohms, and the symbol is XL. The formula for XL is omega L. And you know omega is equals to 2 pi f. Then just put L by the side. This is the formula for inductive reactance. So it's measured in ohms. Okay, that's the first thing to take note. Also, your Ohm's law also applies here. Your Ohm's law also apply. So your V equals to IR. But you cannot write R here because there's no resistor here. What you have is inductor. So you're going to write V equals to IXL. And this is the resistance in this case. So if this one turns to VRMS, this one will be IRMS XL. If this one turns to V naught, this one will be I naught XL. Take note of that. Then the next one, no power loss here. There's no power loss, no power dissipation here. It's only resistor circuits that can have power loss. So no power loss in this case. Then the fourth one is that in this case here, the voltage is leading. So voltage leads the current. You can say V leads I. So that means I is lagging and voltage leads current by the phase angle by pi over 2, or you can say 90 degrees. So if you draw the diagram, the voltage will be leading. Anyhow you want to draw it, does not matter. So let me draw the current first. The current is lagging. Let me not draw the current with this blue one. This one is the current here. So this one will be the voltage. Let me use red for the voltage. The voltage is leading, so I'm going to start it from this top here. So the red one is the voltage. So the voltage is leading. So it will be something like this. And so on. So this is V. This one is I. So you can see the voltage is starting at a higher value when the current is still doing 0. Voltage is already doing a maximum value here. So voltage is leading. So since the voltage is leading, when you draw the vector diagram, this is vector diagram for inductor circuits. Please note this diagram. Hope you are following. Vector diagram. Since the voltage is leading, it's not lagging, it's leading. So the point up, this will be VL, voltage across the inductor, and this one will be IL. You understand? So this will be IL, and the voltage is leading. So draw the arrow towards V, then put the angle 90 or pi over 2. Pi over 2 is the same thing as 90 degree. So I think these are the major things you need to know. So in this one, voltage is leading while the current is lagging. The voltage leads the current by pi over 2. So I think that's all. What else again? So let's check the next part. So let's look at reactance real quick. So reactance is defined as the opposition. So it's an opposition. Just the way you have resistance now. It's an opposition. Just the way a resistor has resistance to that it uses to oppose the current flow. It's the same way an inductor or capacitor has what is called reactance. So these ones, their own resistance is not called, you don't call it resistance, you call it reactance. So inductor and capacitor, they have reactance, while resistor has resistance. You can see the difference now. So what is reactance? So reactance is defined as the opposition. It's an opposition which an inductor or a capacitor offers to the flow of an AC current without dissipating heat. Take note, this word is very important. Without dissipating heat. So reactance is the opposition which an inductor or capacitor. Reactance is only for capacitor and inductor. Nothing concerns resistor and reactance. Okay, reactance is the opposition which an inductor or a capacitor offers to the flow of the AC current without dissipating heat. That is why inductor and capacitor, they don't dissipate heat. Nothing like heat loss or heat dissipation. When you're talking about capacitor and inductor, it's only resistor that has power dissipation. That is why power is I squared R. You can see it's R that is there, resistor. So reactance due to an inductor is called inductive reactance. This is inductive reactance. While the reactance due to a capacitor is called capacitive reactance. And two of them are measured in ohms. Even resistance also measured in ohms. So hope you understand. So this one is resistance, the opposition offered by a resistor. While these two are reactances, the opposition offered by a capacitor and inductor in an AC circuit without dissipation of heat. That's the breakdown behind reactance and resistance. Hope you understand. So let's take an example with our question, and we're having this first example. This is under AC circuits. So the first example, we are told that in this question, we are told that the instantaneous voltage of an AC power supply is given as this. Then we have to find all these guys here. So let's take it one by one. Okay, just remember that the instantaneous voltage of an AC power source is always given as V is equals to V naught sine omega t. This is the usual representation, the general form. Then what were you giving? Give us this one. So all you have to do is just compare two of them. The first question says find the peak voltage. The peak voltage is always what is in front of the sign. Okay, that is V naught. This is V naught here. That's the peak voltage. This is V naught here. This is V naught here. This is V naught standing as 100. So the answer to this question, peak voltage is just 100 volts. Okay, then root mean square voltage or root mean voltage. You know that your VRMS is equals to V naught over root 2, which is the same thing as V naught times 0.707 if you want to use that formula. So my V naught is 100, Abi, 100. So my VRMS now will just be 100 times 0.707. So I'm times it by 100. I'll just move the point 2 times. I'll move the point twice like this. So that will give me 70.7. 100 times 0.707 will give you 70.7 volts. That's the VRMS. So this one is done. This one now, angular frequency. The angular frequency is this value here, omega. They want us to find omega. So if we compare these two things, compare these two guys. This is sine, is this sine. This omega here is standing as 20 pi. This t is this t. So I'll tell you that omega is standing as 20 pi. So the angular frequency, that is omega is just 20 pi. We have to put the unit, the unit is rad per second. Okay, so take note of the fact that angular frequency, don't put the unit as hertz, because they said angular frequency, you have to put it as radians per second. You understand? It's about frequency, how it is vibrating. So you have to put this in as if it's speed. That will be radians per second. Then frequency of the instrument, this is the one that you can put as hertz. Now, to know what the frequency of the instrument, let's compare them back. You have V equals to V naught sine omega t. This is general form. What they give to us, 100 sine 20 pi t. So I already know that this omega here is standing as this 20 pi. So omega is 20 pi. But you know the value of omega now. Omega is a formula. The formula is 2 pi f. So that means 2 pi f is equals to 20 pi. Your pi cancel pi. You have 2f equals to 20. From here, your f is 20 over 2, which is equals to 10 hertz. So the frequency of the instrument will be in hertz. That's 10 hertz. So this last one here is 10 hertz. 10 hertz. So I hope you understand. I'm going to move to the next part now. Alright, so if we talk about impedance, now that's the next part. So if you have an arrow only circuit, a circuit that has only resistor in it, we'll be talking about the opposition will be called resistance. But if you have a capacitor only circuit, the opposition will be called reactance and the symbol will be XC. And if you have an L only circuit, that's an inductor only circuit, you call it reactance, that's XL or inductive reactance. Sorry. Now, what of this impedance now? It will be this impedance. So impedance is when you have the combination of any of these guys. Maybe when you have RC, or you have RL, or you have CL, or you have the three of them together, RLC. In these three instances, the opposition you're going to get, the opposition to the current will be called impedance. The symbol is Z. The symbol of impedance is Z. So let me do an example for RC now. For RC circuit now, the resistance here will combine with the reactance of the capacitor, that's XC. Two of them will combine, then to now form this Z. This Z is called the impedance. The impedance. So when two of them combine, the opposition that they will give, opposition to the current that they will use to block the current, the opposition to the current flow, is what is called impedance. Impedance is only when you have a combination of these guys. If you have a single circuit like arrow, there's nothing like impedance, so you call it resistance. If you have ordinary C, you call it reactance, ordinary L, reactance. But when you have combination of any of them like this, you have what's called impedance. So what is this impedance? So impedance can be defined as the overall opposition. Is the overall opposition, as you can see the word overall, offered to the passage of an AC mixed, taking of the word, an AC mixed circuit. Okay. Hope you have gotten that. Then the unit of that impedance is ohms. Impedance also measured in ohms. Impedance measured in ohms. So let me take it again. Impedance is the overall opposition offered to the passage of an AC mixed circuit. Okay, and the unit is ohms. Impedance is measured in ohms. And the symbol for impedance is Z. The unit for impedance is ohms. Shikina. I hope you understand. So we're going to look at RC circuit now. When you have R and C circuits together, resistor and capacitor together in a circuit, in an AC circuit, what will it be like? What would the waveform be like? What would the formulas be like? Okay, so let's look at it real quick. See the basic formulas for RC circuit. So now you have a resistor, and capacitor in a circuit. So look at the way I'm going to do it. So you have resistor, this capacitor. Two of them are in series. This is the voltage source, alternating voltage source. This is capacitor, this resistor. So this is an RC circuit. There's no inductor here. Now the first thing that you will notice that it's the same current that will pass through all of them. The same current, because they're on a straight line. The current that passed through the resistor will pass through the capacitor. Okay, so that means that IR will be equals to IC. This is the first thing. IR, the current that passed through the resistor, will also pass through the capacitor. So IR equals to IC. That means the resistor current and the capacitor current, they are in phase. Because they are going the same direction. So you can say IR and IC are in phase. Okay, hope you understand. But because they are in series like this, the same current will pass through, but they have different voltage. So VR, the voltage across the resistor, VR and VC, they will not be the same. They will be different. You understand? They will be different because they are on a straight line. They will have same current, but different voltage. Take note of that. So let's take it small. Now, the next thing to note, number 2, that they have different voltages. But because they have different voltages, there will be an effective voltage, which is like the resultant voltage, if you want to call it like that. Now, remember, for the resistor-only circuit that I taught you, the voltage for resistor is going like this, is horizontal. This is VR. Then for capacitor, because capacitor is lagging, the voltage is lagging, it's pointing down. Anytime you are doing VC, voltage across capacitor, if you are drawing the diagram, it must point down. VC must point down because it is lagging. But if you are drawing VL, voltage across inductor, it must point up. Please don't forget why VR must always point like this. So because I have VC and VR is going like this, why VC will point like this. So the angle between them, you can say the angle between them is 90. You understand? So there will be an effective voltage like this. The voltage will come like this. This is like the resultant. This will now be V. So how will you find V? V is just the Pythagoras theorem now. V is the square root of VC squared plus VR squared. This thing, you don't need to cram it. Don't cram it. Once you have VC and you have VR, this is how it will always be. It will just be Pythagoras theorem. You understand? So V is equals to VC squared plus. So what will now be the impedance now? So the impedance Z, two of them are involved. R and C are involved. So there will be impedance. So the impedance Z now will just be, what's the opposition from the capacitor? Should be that's XC. What's the opposition from the resistor? Should be that one is R. Then square two of them like this. That is the impedance. So SC squared plus R squared. Similar pattern. I don't want to cram it at all. SC squared plus R squared. That is the impedance. And the unit of the impedance is in ohms. Don't forget, the unit of impedance is in ohms. Even X going is in ohms. R going itself is in ohms. Okay, so don't forget that one. Then the next one to note is that your normal Ohm's law apply now. Since this is the Z, this is the Z. This is like the total resistance. If you are like doing the whole circuit, like doing as if it's resistor, this will be the total resistance. So that's Z. So if you want to use that formula, you have V equals to IR. So total current that will flow out from here. This is VO. Total current that will flow out from here. You can just do it like this. VRMS equals to IRMS, but you don't write arrow now. You write the total opposition, which is Z. So that is Z. If it's V naught you are using, that will be I naught Z, depending on how you want to use it. The next thing that they will ask you for the power dissipated. The power dissipated. I told you that nothing concerns capacitor and power dissipated. It's always resistor. Anything power is always resistor. So average power, the average power. Take note, average power. You just do your I squared R, but the I you are going to use here is IRMS. So don't go and do I naught squared R. You will miss ammo. It is IRMS squared. The I you're going to use is RMS value. Then the normal resistor. So there's power dissipation here because there is resistor in the circuit. We are doing RC, so there will be power dissipated. But the power that is being wasted is not from the capacitor, it's from the resistor. I told you that capacitors don't waste power. Inductors don't waste power because they don't have resistance. You understand? It's only a resistor that dissipates power. Next one, 0.6. The next one is something they call the phase angle. So phase angle. See the way I'm going to get it to. It's very simple. Phase angle is very simple. Just write phase angle. The symbol is phi. So you will say tan phi. Now you can get this phase angle using two methods. You can get it with voltage method. If you want to remember it, you can get it with voltage method. The easy way to remember it, voltage method. And there's one they call opposition method. Opposition method. So if you want to remember it, if you're using voltage method, what do you have in this circuit? CB is V, is capacitor, and R that you have. So if you're using voltage method, this formula for tan phi, now, this phase angle, it will just be, make sure you always put resistor under. So that will be VC, that's voltage method, then over, put your VR under. Assuming I was doing L and R now, it will be VL over VR. The R must always be under. So that will be VC over VL. That is tan phi. So I'll now do phi. Phi will now be tan inverse of VC over VR. Then you can work that one out. But most times, it will be very straightforward for you. They will give you something that if you can easily do the tan inverse because calculator is not allowed in JAMB. Hope you understand. But if you're using the opposition method, you're going to be using their X, C, and R. So opposition method now, that will be tan phi will be equals to, I'm using opposition method though. So I'll be talking of reactance. So that will be XC over R must always be under XC over R. So if you're using voltage method, you can easily remember, just put the V at the top, VC over VR. If you're using opposition method, tan phi is also XC over R. Then just go and do the tan inverse and get your answer. The next point is if they ask you to do what is called the power factor. Power factor of AC circuit is always constant. That one, the formula is R over Z. No matter where you are doing RC, RL, no matter the one you are doing, the formula is R over Z. Power factor. And the power factor, what will be in front is cos phi. Cos phi is R over Z. That means after getting, you can also get phi from this formula. After getting phi, just do the cosine. That's when phi is 60 degrees now. You now do cos 60. Cos 60 will now be the power factor. The power factor is the cosine of the phase angle. You understand? This thing here is called power factor. This is the power factor. Power factor, the cosine of the angle, of the phase angle, is the power factor. And that is formula R over Z. So you can also get power factor from here too. Just go and do tan phi equals VC over VR. Then you now do phi equals to tan inverse. So once you got in that phi, let's assume the phi that you got was 30 degrees. Then you're now going to do cosine of 30 degrees. That will give you the answer. Or just look for R and look for Z. Do the power factor. Divide it together, R over Z, and you get your answer. So then average power. How far now? Average power. I think we have done it before. Average power. We don't do it before. So that's I square R. The I there, please, the I is not I not o. Now I RMS you go use. So these are all the key points you need to know. These are all the key points. These are all the key points that you need to know. So that's it. Real quick, we have done RC, right? I've done RC circuit. So let's look at RL. The pattern is the same. You don't need to stress yourself. So draw your resistor first. This is your resistor. Draw your inductor. Inductor is a coil. Bring it down. Draw your alternating source. Draw here like this. Bring it down. If you like, you can put ammeter here. Does not matter. Then put voltmeter across each of them. That will not matter. So what you could just do now, we say the next thing to do now is label it. This is R and this is L. This L is the inductance of the inductor. This R is the resistance of the resistor. So the first thing to note in this place, you see that it's the same current that will flow through now. To be all of them did the same line. This current that will flow here, and then go flow past all these three guys, these two guys rather. So that means IR, which is the current through the resistor, it will be the same. It will be the same as the current through the inductor, which is IL. Because two of them did the same line now. Abi? Okay, now the next thing now be say, that means if you draw the diagram, IR, the phasor diagram, IR and IL, two of them go there in phase. That means IR is in phase with IL. Hope you understand that one. That one don't go like that. Now, for the second one now. The second one is, let's get our diagram. For our diagram, I want to get the vector diagram. I remember what I tell you about inductor voltage. Inductor voltage always lead, so it always points up. Inductor voltage always points up. Let me just reverse and fast. Capacitor voltage always point down. VC always points down. VL must always point up. VL must point up. Why? VR must point like this right hand direction. Okay, so hope you don't remember that one like that. So let me just quickly draw the phasor diagram. Just draw your VL. Draw it up. This is VL. Then draw your VR like this. So the vector, the resultant of the two of them go there like this. This is now the V. So this V could just be Pythagoras theorem, normal way now. So effective voltage, now total voltage will be VL plus VR. You go square both of them. Then put square roots there. That is effective voltage. Hope you understand that one. You need to cram out. You need to cram out. If you compare with one for VC, nah, the same thing, two of them be. Okay, now let's go to the third one now. The third one is to get the Z. You know, this is Z will then take place because we have L and R. So there will be Z, there will be impedance. Then the Z now, just look for the opposition now. Z is about opposition. So I'm looking for XL, then I'll look for R. I will square two of them, then I will plus them. Okay, that is the Z. Assume I do R and C now. In the same way, I go do XC. I go do R. I go square two of them. I go square root them. So this was the same pattern. I need to cram them at all. So that's that about Z. And the unit of Z is ohms. So don't forget the unit of Z now ohms. So since that Z is the total impedance, total resistance where this circuit go give to the current flow. That means if you don't compare it with Ohm's law now, if you compare it to Ohm's law, V equals to IR, that's Ohm's law. But you don't go write R now. But the total impedance is Z. So if this place not turn to RMS, here go change to IRMS. If this V turn to V naught, this one go change to I naught Z. You understand now? Normal pattern. Then phasor diagram. No waste your time. No stress yourself. When they ask you for the phasor diagram, I think I've done phasor diagram. Phase angle now. No do yourself a phase angle. Phase angle. I told you that there's voltage method, and there's opposition method. You can use it here. It will also work. No waste your time. It can also work. So for voltage method, since I have, then give me now L and R. So voltage method, I'll just do tan phi. I'll do VL. Anything resistor must be under VL over VR. That's voltage method. I can also do tan phi. If I'm using opposition method, that's the resistance method. That will be XL over R. I'm using the resistance method, so the two of them will work. That's your tan phi. Hope you understand. Now let's go to power factor. Power factor. power factor constant now. I don't tell you the formula before. That one need a change. So 6. The power factor is cos phi. So that one is always R over Z, like I told you. It's always R over Z. Or if you like, it's another formula, VR over V. But just remember this one be fast. R over Z, fast. Or VR over V. That will give you the power factor. And the power factor is cos phi. Take note, the cosine of the angle that I got from here. You understand? Then average power. There's power dissipated, I hope you know. Because the resistor and L are together, they're in series. So no power dissipation in inductor. Nothing concerning power dissipation in inductor. Power dissipation is only for resistor. So because there is resistor there is power dissipation. So power loss, dissipation. So the power loss, cannot say P is I squared R, Shikina. I squared R. But that I squared R, you can also call it average power if you like, average power. But that I squared R, the I you're going to use there is not ordinary IO, is the RMS value. Take note of that. Then effective voltage, I think I've done it before. Effective voltage, just look for VL, look for VR, square 2 of them, do the square roots. You can see this is the pattern, they similar to, even the grammar, just the change. You just be changing it and you still be getting the same answer. So let's go to capacitor and inductor now. So hope you understand this one. This one is RL. So the circuit containing C and L. Okay, C and L only. So capacitor and inductor only. So that will look like this. Capacitor, your inductor. So two of them are in series connected to your alternating voltage source. So your inductor is L, right? Your capacitor is C. Okay, so this is the inductance. This is the inductance and this is the capacitance. Take note of that. Now, the next thing to note is that maybe they are in series now. Since they are in series, the same current will flow through. That means, number one, IC is the same thing as IL. So that means IC is in phase with IL. Okay, keep that in mind. The vector diagram will just be like this. IC going the same direction as IL. That one, no, there's no issue about that. Number two. Now, they're in series, so that means you have these different voltages. You have different voltages. And I told you earlier, voltage for inductor is always going up. That's VL. Then VC is always going down. Remember now, I told you, right? So this line here, this one here will be IL or IC, since they are the same. IL and IC are the same. This will be IL and IC. So you need to find the final voltage, like the effective voltage, the final one. But notice that you're not using this part though. Since you're looking for voltage, nothing concerning you on this current side. So you are looking at this line here. So since the voltage in the inductor is always leading, it's pointing up. So this is the one that will win, like the upward direction will win. So that's why the V effective or total voltage, anyone want to call it, V effective will just be VL minus VC. You're not doing square roots this time, or nothing concerning on square roots. So V effective V is just VL minus VC. Then if you are doing your Z, your impedance, if you are doing impedance Z will just be XL minus XC. Please, it's XL that will subtract XC. It's not XC minus XL. So XL will subtract the XC. VL also subtracts VC. When you are doing L and C, most of the time you're not doing anything squared. You're not like square roots here. So it's just normal subtraction. Since two of them are in the same vertical direction. So for V, VL minus VC. For Z, XL minus XC. I hope you understand that one. So after that line, you can now get your normal Ohm's law. So from your Ohm's law, you can have V cos IR. But you're not writing RO. You're going to write Z. V cos IZ. The Z is this value here. So because you have VRMS here, this one will be IRMSZ. If you have V naught here, this one will be I naught Z. Just be changing it the same way. Then we have already done V. So the key point here is like this is V. V is VA minus VC. Z is XL minus XC. You're not squaring anything. Just minus them normally. Then your VRMS is I IRMS Z. V naught is I naught Z. So that's all. Okay. So we're going to look at the one that will involve the three of them now. The three of them in a single diagram, like RLC. One or the last one, which is a combination of R, L, and C. So you have your R, you have your inductor, then you have capacitor. So this is RLC circuits. Then connected to an alternating voltage source. Then just like that. So this is the resistance, this is the inductance, this will be the capacitance in farad. So take note, take note. Unit of this resistance is ohms, unit of inductance is Henry, unit of capacitance is farad. So if you notice something, it's the same current that will flow through all of them, the same current that will flow through all of them, the same current, the same current. So that means my number one, IR, current through resistor, will be equals to IL, current through inductor, which will be equals to which will be the same as current through capacitor. So that means three of them are in phase. The three of them, IR, IL, IC, they're in phase. They're going the same direction, and they are also equal. All right, that's that. Second one. Now, how will we get the V? So let's get our phasor diagram. Remember how to draw it to VR. I told you VR is always pointing to the right, Abi. This is VR. And I told you that VL is always pointing up. Then VC is always pointing down. So you know that these two are dragging. They are dragging in the vertical direction. Like who's going to win? I know it's VL that will always win. VL will always subtract VC. So it's VL that will win at last. So once VL wins, you have a line going like this. This will be the effective voltage. So the effective voltage will be a gap here. Let me just put it like this. A gap here and a gap here. So it's this gap that you need, this distance that you need. This distance here will be VL minus VC, because it is VL that will win. The upward direction will overcome the downward direction. VL will win over VC. So that part will be VL minus VC. So you're not doing Pythagoras theorem between this one and this one to get the ordinary V. I hope you understand. So V now will be VL minus VC. Square it. Put plus. Put your VR. Then root everything. Don't forget to put square there. So this will be of V. Okay. I hope you understand. Let me just write it again. V equals to VL minus VC squared plus VR squared. Then everything square roots. Then that's number one. That's number two. Let's get number three. Let's get Z. So what will be Z? You know, I told you that when you have that's your impedance in ohms. So if you are doing for Z, XL, your XL and your XC, it is XL that will win. So you have XL minus XC as the winner. Then you now have R. So this will give you your Z. So that means you square these two guys, XL minus XC. Square it first. Plus it to the square of the resistance. Then that will be Z. Then root everything like this. Are you following? Are you following? So once we have gotten our Z, the next one is to do your, let me say 4, to do your I, V equals IR. Because of IR, you can put it as Z. That will be V equals to IZ. So V equals IZ. If this one turns to V naught, this one will be I naught Z. If this one turns to VRMS, this one will be IRMS Z. Yes, I'll just be changing it like that. Okay, so what else again? Power dissipated. There will be power loss now. Should be there's resistor there. Power loss or power dissipated. So average power. Normal I squared R. That's the power. Average power I squared R. But the I is RMS, so don't forget. Which one again? Which one again? I think that's all. Power factor. Oh, power factor. Not true. Not the power factor. Power factor. That one is R over Z now. Don't need to waste time. Power factor is R over Z. Abi? Then to get your tan phi, your phase angle. Now let me consider one, sorry. To get 7. 7 is the phase angle. Hope you are following now. Phase angle. So which method should we use? Let's use voltage method. voltage method. So I'll look for the old V. Since I have RLC, these two we drag together. I'm going to get VL minus VC out of the two of them, and I must always divide by VR. This will be my tan phi. But if I'm using opposition method, I'm going to be using XL and XC. So opposition method now. Opposition method, that will be my tan phi. That will be XL. XL will subtract XC like I told you. Then just put arrow under. So these are the things you need to know. Then the next one is take note of something, that the power factor for a pure resistance is 1. Don't forget that power factor cos phi. I told you that cos phi is R over Z. So if you have a resistor, it's a circuit that is just a pure resistance circuit, as in it has only resistance, the phi will be 0. Hope you know why the phi is 0. I told you that the current and the voltage in a resistor circuit, they are in phase. They are in phase. And if you watch from the first part, I told you that the phase angle is 0 for a resistor-only circuit. A circuit that has only resistor, phase angle is 0. So if you follow this formula, since the phase angle is 0, if you do cos of 0, you will get 1. So for a pure resistance circuit, the power factor is 1. Since the phi is 0, then cos phi will be 1. Cos phi is the power factor. So if you have a circuit, or yes, a circuit that has only resistor, you say the power factor is 1. You understand? But if you have a circuit that contains only inductor, if it has only inductor, or it has maybe the capacitor, the power factor will be 0. Why is it 0? Don't forget that if you are doing inductor circuit, the current and voltage, they are out of phase. Like in this inductor circuit, the VL is leading the current. So the phase angle is 90 degrees. So they are out of phase by 90. Then if you are doing capacitor, the capacitor current is leading the, or let me say it's greater than, is leading the capacitor voltage by the same 90 degrees. So that means my phi is 90 degrees here. The same thing here, phi is 90. And when you do power factor is cos phi. If you do cos 90, since phi is 90, cos 90 will give you 0. That is why the power factor of a circuit that contains an inductor only, or it contains a capacitor only, the power factor is 0. But power factor of a circuit that contains a resistor only, the power factor is 1. Okay, I hope you understand. The next part will be resonance, and that will be the end. Then we'll take some past questions. The last part is resonance. Okay, resonance in an AC circuit. So normally we're looking at RLC as an example. So you know your RLC has a resistor, it has an inductor, then it has a capacitor. All of them in series, connected to an alternating voltage source. Okay, that's the frequency. Now listen to me. Now at resonance, you want to know when will the current be maximum or when will the current be minimum. So at resonance, the impedance is minimum. Take note, at resonance, I'm going to tell you why. The impedance is minimum. Now see why it is minimum here. This is resistor. This one will offer XL. This one will offer XC. These two guys will combine as XL minus XC. The opposition that you have here to the current flow, the opposition to the current flow are R and XL minus XC. So you have two things opposing at the same time. Two oppositions, the resistance and the reactance, opposing the current flow at the same time. So that means the current will be minimum. Okay, that means the current will be minimum at that particular point, because the resistance is high now, so small current will flow through. But for maximum current to flow through, one of these guys must, like this guy must be equal. This one must be 0. That's what I'm trying to say. So once this one is 0, it will now be only the resistor that will be opposing the current flow. So because the resistance has reduced, Okay, or you can say because the impedance has dropped, then the current will now be large. So initially, you have R and XL, XC opposing the current flow. The current is going to be small current. But once this one disappears, once XL minus XC disappears, it will be only R. So because the opposition is now small, a large current will flow through. I hope you understand the pattern. So resonance occurs when XL is equals to XC. Take note, resonance occurs when XL is equals to XC. Sorry. And at this point, the impedance, the opposition, the impedance is minimum. Okay, so from your impedance formula for RLC, you have XL minus XC squared, then plus R squared, everything here, all squared. But because we are saying XL is equals to XC at resonance, that means these two guys will cancel out because XL and XC have the same answer. So each one will give you 0. So you just have Z is equals to square root of 0 plus R squared, which is the same thing as Z is equals to R squared square root. So this will give you Z is equals to R. So this is another thing to take note of. At resonance, what do you have? Number 1, XL must be equals to XC. Okay. Number 2, impedance is minimum. Number 3, the impedance is equals to the resistance. Okay. Then number 4, maximum current will flow. Maximum current flows at resonance. So yeah, these are those 4 things you need to take note of. Then so because XL and XC are the same, you can get a formula that will give you the resonance frequency. You understand? Because your XL and XC, 2 of them are the same. So what is XL? XL is omega L. What is XC? X is 1 over omega C. Okay, so from here, your omega is 2 pi F. This is 2 pi FL. It's equals to 1 over 2 pi FC. So by the time you square everything, like take everything to this side, like cross multiply like this, you have 2 times 2, that will give you 4 pi squared F squared LC. There will now be 1. So I want to make F zero the formula. So it will be F squared is equals to 1 over 4 pi squared, then LC. Then from here, I can do square roots. F will just be square root of everything here. 1 over 4 pi squared LC. Then you can just simplify it to square root of 1, 1. Square root of 4, 2. Square root of pi squared. Square root of pi squared is pi. Then let this root be only on top LC. So this frequency at this point is called the resonance frequency. So that means you need to take note of this formula. Note this formula. Resonance frequency is 1 over 2 pi root LC. That's the 4th thing to note here. Sorry, the 5th thing to note at this point. You need to know that the resonance frequency F is equals to 1 over 2 pi root LC. This is F naught, resonance frequency. Okay, so I hope you understand. So if you draw the graph will look something like this. Like if you draw the graph against frequency to look like a bell, like current. This is the frequency here, and this is the current. You notice that the current is maximum. This is the current here against frequency. You notice that the current is maximum. You can see the bell shape. This is the bell shape graph. So the current at this point here, this is the maximum current, and it will occur when the frequency is the fundamental frequency. That is when the frequency is equals to 1 over 2 pi root LC. Okay, so take note of this 4 stuff. JAMB they have asked it before. This stuff here, this 5 stuff here. At resonance, number 1, XL must be equals to XC. Even VL gone safe is equals to VC. Let me just add that one for you. At resonance, VL is equals to VC. Okay, at resonance, XL equals XC or VL equals VC. The impedance is minimum. The impedance is equals to R. Then maximum current flows at resonance, and the resonant frequency is 1 over 2 pi root LC. Okay, so I hope you understand that particular point.